Hello, and welcome to KAUST Live. The growth of mobile technologies, cloud computing, streaming services, and more is placing increasing demand on global networks. And how we meet these demands now and in the future is a topic of substantial interest. In fact, it's the research focus of today's guest, KAUST doctoral student, Qurrat Ul Ain Nadeem. Thank you for joining us, Ms. Nadeem.
Thank you very much.
So set the stage for us. Talk about the big picture of network traffic and how you came to be interested in it as a research topic.
Okay. So historically, an online presence on the internet was enough for broadcasting and collection of information. But recently, these social networks like Facebook and Twitter and these video streaming applications like YouTube are generating new forms of social interaction and collaboration, most of which happens over existing cellular networks. This evolution in the social networks and the web-based applications has led to a growing number of mobile broadband subscribers who require real-time connectivity and consume bandwidth-hungry video content. So this has led to this huge exponentially increasing explosion in the data traffic, the wireless data traffic, with the amount of wireless data handled by the cellular networks expected to increase 500 exabytes by 2020. So in the last decade, most of the research has gone into identifying the technologies that can meet this explosion in the wireless data traffic. And I was particularly, when I started my PhD, I was interested in something that does not bring an incremental improvement in the existing performance of the systems, but can actually dramatically improve the performance. So there were a bunch of technologies in their infancy at that time, and I picked one of those, and I knew it had a lot of commercial applications because the industry was the one that a lot of industrials were actually looking into it. So I thought it would be a good idea if someone from research or academia picks it up and tries to bridge the gap between the industry's vision for these technologies and the theoretical research that can help in improving or realizing the gains that can be that we can get from these technologies.
It seems like such an almost double challenge because there's both the growth in the amount of and complexity of the content, but then also the amount of people in the world that are accessing this content. Talk about which of those is adding the most to the network traffic.
Absolutely. So actually both of them are kind of correlated, but the idea is that 5 years ago there was a report that said that by 2020, the next generation of networks, 5G networks, are going to connect 50 billion devices, which is a huge number, trust me. I mean, it did not seem possible 5 years ago, but it's actually happening. So the amount of data and the number of users are actually, they go together, right? So this is actually the vision of 5G, and this is what we have been trying to do, to realize this grand Internet of Things picture, connecting billions of devices, not just smartphones, devices, things everywhere.
And that gets to an interesting point. So 50 million devices obviously isn't, several million people with thousands of devices. It's lots of Internet of Things. To what extent does your research sort of get into Internet of Things, understanding that network growth and such?
So if you talk about my research, it actually, the topic that I worked on, it's very technical, it's full dimensional, massive MIMO, forget about the complicated name. But the idea is to increase the number of mobile broadband subscribers that are served within the same time frequency resource. So the idea is to multiplex several users much more than there used to be in the conventional 4G LTE systems, and serve them in the same time frequency resource utilizing the existing cellular networks. So my particular result and research actually showed that you can almost double the number of mobile users that were used to be served by the conventional systems.
You talked about 5G. So what is 5G, if there's a way to explain that, and how will it be implemented in the future? How is it different than, like you said, 4G LTE that we use now?
So to understand 5G, I think it's a good idea to talk about the previous generations and see how it is different from them. So 1G brought us the first cell phones back in the 80s. 2G let us text for the first time. 3G brought us online. 4G provided us with the speeds that we enjoy today. And now we're talking about 5G. 5G needs to go further, much further than just faster data rates. 5G is not just about connecting today's smartphones. It's about connecting tomorrow's homes, vehicles, robots, cities, virtually everything. In fact, like I said earlier, 5G is expected to connect 50 billion devices by 2020. And to connect these billions of devices, 5G needs to meet these extreme variation in requirements as compared to the previous generations. Like it needs to scale down in cost and power. It needs to scale up in performance by providing mobile broadband that is not only faster, but also more uniform. And it also needs to improve in reliability and latency for mission-critical services like autonomous driving or healthcare sensors. You cannot afford to fail in such circumstances. You cannot afford any delays in such circumstances. So yeah, so 5G is pretty different from the previous generations, like I said. And to talk about what exactly is 5G, 1 year ago, probably there was no answer to it because all the technologies were still being worked out. We didn't know what would work and what would not work. But right now, the standard on the 5G has been completed, and there are 5 brand new technologies emerging as the foundation of 5G networks, which include, for those who would understand, millimeter waves, massive MIMO, beamforming. Massive MIMO plus beamforming is my area. Then you have full duplex communications, and lastly you have what? You have small cells, yes. So these are the 5 technologies that constitute 5G.
Speaking cosmically, like where does this growth or expansion in network traffic end? I mean, is there a point at which it wouldn't even be feasible to service the traffic, or will there always be, in your idea, sort of a technological solution to the challenges that we create wanting more bandwidth?
I think there will be. And so far, we have been able to come up with solutions to tackle this exponential growth. And I think this vision of connecting like things, billions of things, I mean, I think it's doable, and it can also be extended for systems beyond 5G. I mean, there is always something more to do. Nothing is impossible in research.
Is there a 6G already sort of in the imagination of researchers in your field? Or?
Yes, people are now talking about beyond 5G networks, which is like going towards the 6th generation. And actually, you will see documents coming up on the internet on these 6G networks. But I think we should try to first fulfill this 5G vision before moving on to the 6th generation. You talked about a few of the technologies, and I think satellite technologies are sort of integral to 5G, as well as you said, higher frequency waves. Why is that necessary to get to the next level with network traffic? Okay, so we have this problem of we don't have enough spectrum available for use at the current frequencies that we operate. So the idea is to move to these millimeter wave bands where you have many other advantages. At millimeter wave bands, you're able to pack a larger number of antennas within the spaces that you have available at existing base stations. And for those, like in very simple words, the higher is the number of antennas you have at the base station, the more are the number of users that you can serve, the higher is the capacity that you can achieve. So this benefit that comes from operating at millimeter wave bands is like a huge breakthrough.
And you're able to focus traffic in a more specific way. Am I right about that? So you're able to sort of, if you notice that users are congregating in a specific place, sort of redirect resources. Talk a little bit about that.
So yeah, so that's actually what my work is. It's beamforming. So currently, the existing networks, they have a static beam pattern, which means that, you know, when there is an antenna, it radiates energy. So all the current antennas, they radiate energy in the horizontal plane, in the azimuth plane. So all the users in the cell receive the same kind of energy, and they utilize this received energy to detect their signals and, I mean, all that kind of stuff. Now the idea, the technology that I worked on, it actually allows you to do beamforming, which basically means that instead of having this omnidirectional energy in the whole plane, you send these directed beams towards the user that you're trying to serve. I mean, if I'm trying to serve you using a base station, instead of radiating energy in this entire room to people who don't even need it, I would actually make a beam and concentrate that energy towards you. so that you get a better signal reception and you do not face interference from other users. So this is the idea. This is one of the key technologies that help realize the 5G vision of serving more users with a better quality of service.
And so is this how they're starting to talk about three-dimensional, is this beamforming, or talk a little bit about that?
Okay. So the current beamforming methods, not the current, actually 2 years ago, because now I work on 3D beamforming. So when I started, the beamforming methods were only limited again to the horizontal plane. So you make these beams only in the horizontal plane.
Yeah.
So if you are located here and there's another user located on the 3rd floor, I'm not separating the beams in this dimension, in the Z dimension, in the elevation dimension. I'm only separating you both in the horizontal direction. But if you both are exactly at the same point in the horizontal direction, you're going to face a lot of interference but with 3D beamforming, what we do is we not only direct these beams in the horizontal plane, but also in the vertical plane. So you have these elliptical beams that there's one beam here, and then you send one beam there and one beam here to people on the lower floors and people on the higher floors to enable a better separation between you guys.
Right. Fascinating. So and so what I'm hearing of this is that there is a theoretical sort of place that service providers want to go to with a very high density per square kilometer, upwards of 1 million people. I mean, how is that even going to be possible?
So this number again goes with that same idea of 50 billion people.
I see.
And of course the density is very important. So the idea is that when you have these dense crowds of, because you see you have these urban settlements and rural settlements. In the rural areas, I mean, I think existing beamforming methods are sufficient. But the problem of this, having this high density of served mobile users, comes particularly in urban settlements where you have these high-rise buildings. You have to separate the users between different floors of buildings. You have concerts, people complain about poor signal reception at concerts and at stadiums watching matches. So these kind of technologies are particularly useful there. So what you can do is, like, you can have multiple base stations in such areas. You have this idea of small cells. So you divide an urban settlement that previously used to be considered as one cell of a particular radius. You divide them into several smaller cells, and you deploy more resources there. You deploy more base stations there to enable better signal reception at the users. Then you use my idea, which was of 3D beamforming, to enable better separation of the users in the buildings or in the stadiums through these directed beams. So using all these technologies, particularly I would say small cells and full dimensional MIMO, you can actually realize this high density of, you can actually serve this high density of users in urban areas.
Yeah. How did this concept, this solution come about?
Full dimension MIMO, what I work on?
Yeah.
So basically it is a combination of massive MIMO and beamforming. So like I said, when I talked about the millimeter waves, the idea now is to have a higher number of antennas, because kindly it's like the more the number of antennas you have, you can get higher capacity gains, because it scales like linearly with the minimum number of antennas you have at the transmitter or the receiver.
But these waves don't reach as far, am I right about that? So the 5G, the sort of higher frequency waves, don't reach physically as far, right?
Yes, absolutely.
Okay,
so millimeter waves have this problem of shorter propagation distances, and they get obstructed by buildings and like these kind of things easily. So my research is not on millimeter waves, because personally I believe that you can even like rely on the lower frequency bands and use this massive MIMO concept by not facing the disadvantages that come with millimeter waves and still multiplexing a higher number of users. So this technology, like I said, it's basically, with massive MIMO, you have a problem that you don't have enough space available at the base station. You cannot install like a large number of linear arrays. I mean, you just have a tower. How many antennas can you install in the traditional linear fashion? So the first idea was to actually arrange these antennas in a 2D array. Because when you distribute these antennas in a 2D array, you actually reduce the overall width of the array. And mounting this 2D array is easier as compared to a linear array, because you have enough space to mount this 2D array. So this way you realize the massive MIMO idea. You have many antennas, but instead of having them in a linear array which cannot be installed, you can distribute them in a 2D plane. Now, the second idea is that instead of having passive antennas which cannot do beamforming, which have this constant radiation of energy, you can have these active antennas, where basically you tune each antenna element separately to get a particular beam shape from that antenna. So combining the massive MIMO idea with this idea of using active antennas, you basically realize full dimensional MIMO, where you get the gains that are promised by massive MIMO, and you also get the gains promised by beamforming.
Right. Do you see AI then being sort of a meta controller of these things? I'm imagining dishes moving and things to create these 3D beamforms. Is there going to be sort of higher computing that's going to be needed to run these as well?
So there are two things. There is one thing known as the mechanical tilt, where you actually physically tilt these things, which I think is pretty hard, and it's not feasible doing that again and again, because you have to change the beam pattern at every transmission. I mean, the user can move somewhere else. I mean, there can't be someone who can, or you cannot have this whole circuitry to enable this mechanical tilt of the elements. So the idea is to keep the mechanical tilt fixed and actually use this idea of electrical tilt. So you apply these phase shifts to these elements, and by changing the phases between different elements of the array, you can actually realize different beam patterns. So you don't need to do it physically; you can just do it electronically. Of course, still it imposes more complexity. You're absolutely right, but I think it's manageable. It's not something that's beyond what is being handled by the current systems.
Yeah. So all of this is leading to, of course, you were recognized recently by the Marconi Society, and you've just literally today come back from that trip. Tell us a little bit about that experience and what you were awarded for.
Okay. So the Marconi Society is the most prestigious, or at least one of the most prestigious societies that honor individuals from the fields of communications and networking. It was actually founded by the daughter of Marconi, who is the inventor of radio, to honor her father's work on long-distance radio transmissions. So they basically support and acknowledge and recognize scientific contributions in the fields of communications and the internet, which largely benefit the mankind. So they have the senior award, the Marconi Prize, which goes to someone who has accomplished something extraordinary in this field. Like this year, the winner was Dr. Tom Leighton, who is basically the founder of Akamai, and he is the pioneer in the field of content delivery. And previously, Windsurf has gotten this Marconi Prize. He's popularly known as the founder of the internet, and Martin Cooper, the inventor of the cell phone. So for me to be there, under the same roof as all these big names, I mean, for someone like me who specializes in communication fields, we have grown up hearing the names of these people, and to be in the same room as them, that itself is a huge honor. And on top of that, getting this Young Scholar Award and presenting my work in front of them and answering their questions and having my work appreciated by them, it's something unbelievable. I mean, I'm really, really excited and really honored to be a part of this society. And this Young Scholar group, it's an incredible group of people who are 27 years or below of age. 27 years because that's the age when Marconi invented radio.
I see.
So that's the significance of the number. So students some of them have already completed their PhD, and they have accomplished something extraordinary at such young age. They are the ones who are acknowledged by the society and who are given this Young Scholar Award, and they make this incredible group where they work together and they come up with practical solutions for problems that are being faced by the current communication systems. So it was a huge honor to be there, to be to be a part of this wonderful group now, and I hope to work with them in the future. Yeah.
Where was the event held?
It was in Bologna, Italy, which is basically the birthplace of Marconi, and that's where he did his first long-distance radio transmission. So the place holds a very important value in our field.
I see.
Yeah.
Okay. How did you get interested in STEM? What started that journey for you, and then how did that eventually end up in graduate study here at KAUST?
So for me, I have been always good at science. For me, there was no like life-changing moment when I decided, oh, I need to get into sciences. This is my area. I've always been good at math. I've always known that I need to pursue an undergraduate degree in either math or physics or electrical. The thing was, I was good in both math and physics, so I wanted to do something that uses both. And I am more into things that are of practical relevance. So I thought maybe engineering is the way to go rather than majoring in pure physics or pure mathematics. So right from my high school, I knew that I had to get into the best undergraduate school in my country. And my parents were very supportive actually, because in Pakistan, if a girl is good in academics, you have to make her a medical doctor. But thank God they didn't force me. It's actually a thing. I mean, when I chose to do electrical engineering, my whole family was like that, oh, this is not a good field for you, why are you doing this? But yeah, my parents were very supportive. I got into LUMS, which is one of the best research institutes back in Pakistan. And like most of the students there end up at places that are very good, like all my batchmates. So for how did I get interested in graduate studies? That was when I actually entered my undergraduate studies. I realized that I wanted to get into academics. I was not a kind of a person who could work in an industrial environment purely on making like hardware designs and protocols. I liked theory. I wanted to do some theoretical research. So I knew that I had to get into academics, I had to get a Ph.D. So I started applying for Ph.D. programs at different graduate schools, and I got into several good schools, including Cornell, Wisconsin, and KAUST. All three were fully funded PhD programs. It was a hard choice. But then I decided to go for the best advisor. And luckily in KAUST, I had the chance to work with Professor Aluini, who is a big name in our field. And the experience was actually rewarding. And for me, KAUST was actually a new place then. It was 4 years old, I think. So I knew that, and I read about it, I talked to people, and I knew the kind of opportunities and the kind of research facilities they're providing to the students. So I knew that if I come here, if I work hard, if I play it right, I will be able to make a bigger impact in my field. And that's what happened. I came here, I got individual attention. I worked with Dr. Abla. She's a research scientist in our group, and we would work nights solving problem before I got married. So I would spend like hours with her till like 3 a.m., 4 a.m. and I got a lot of attention from her, and she actually taught me the basics of my field. And I built upon that to solve all these problems. So honestly, I think KAUST and Professor Aluini and Dr. Abla have a huge part in this award. I really, really owe it to them.
Well, what lab in particular do you work in on campus?
It's Communication Theory Lab.
Okay.
Yeah.
Talk a little bit about the work that you do there that's then led to your papers and things.
So Communication Theory Lab, it's led by Professor Aluini, and it's constitutes of a couple of research scientists, postdoctoral fellows, and PhD candidate students and master's students. And all of them are focused on solving problems in the fields of communication theory and networking. Largely doing performance analysis of different technologies, and recently we've also a couple of students in the group have also started to bridge the gap between theory and practice, and have started to implement the technologies in practice by collaborating with other groups who deal with hardware technologies. So yeah, and what happens is generally Professor Aluini, he assigns every student to a postdoctoral fellow, and then that fellow guides the student, and they both work out a potential topic that they can work on. So I worked with Dr. Abla, and when I started working with her, she had just joined KAUST, and previously she used to work for Orange, which is one of the biggest telecommunication companies in France. She was the one who actually heard of this technology. It was really, really new. There was nothing on it. When I started working on it, there was nothing, no papers. I was the first one in academia to pick this up. I had to read these boring industrial reports that, trust me, would not make any sense to even like people with 20 years of research experience. It was a nightmare to even understand those reports. And then to build upon those reports, to find out the missing gaps that need to be filled, that was the real challenge. And that we both tackled together.
How close to implementation? I know that in a couple of cities in the US, 5G is just starting to get implemented, if that's even the same definition that you have as 5G. But how close to being implemented are some of the things that you've been working on, do you think?
Okay, so Qualcomm is like one of the leading telecommunication companies that is like paving the way towards 5G. So they have developed their first millimeter wave antenna modules that, like I said, is a key technology in realizing the 5G vision, and they have made those modules available to their smartphone partners. So now the testing is going to begin. Some test beds have already been laid in China and the US, and we have some measurement results, some very promising measurement results that show that the technology is actually viable and can actually achieve the promised gains. So the standard was completed in June this year. And now since the standard is complete, which means that all the telecommunication companies can work together and can actually compare and see their results with this benchmark that has been set by the 3GPP standard. So if all goes according to the timeline set by the 3GPP and all these leading companies, I think by early 2020s, you are going to get your first 5G capable phones. I hope they work.
Very cool. I hope they do too. Yeah. Well, thank you so much for coming to speak with us. That's all the time that we have for today. But join us every Wednesday at 4 as we explore the people and the science that make KAUST unique. Remember to comment, like, and share on all the KAUST social channels. And from everyone here at KAUST, thank you so much for watching.
Thank you very much.
Much appreciated.